Shalom, BlueHat. So you might think because I'm up here on stage at a security conference that my expertise is in security. But in reality, my true passion is kebab. And I can tell you, without a doubt, the best kebab in Israel is in Haifa. You get the amba, you get the bread, it's amazing. So when I had the opportunity to speak here at BlueHat, and this is my fourth BlueHat, I'm one of the select few, Kiwi. The other folks that have come here, one of the things that keeps me coming back is the energy and the enthusiasm. This really feels like the Eurovision of security. You walk in here, in 10 seconds, Sar's asking me about Hyper-V fuzzing. I see Luca talking about jailbreak. It really is a great energy here. And so when I thought about what I wanted to talk about, it's really getting back to my research roots. So about 12 years ago, I joined Microsoft as one of the first folks kind of doing full-time pen testing in Windows. And just recently, I rejoined that team, and I was amazed at the progress that's been made in the last 12 years. So I thought I would kind of share some of that with you and where we're at today. We have 5.7 million source code files. That's not lines of code, that's source code files. And if you look at some people's code, they got that 10,000 line function in there. There's quite a few lines of code, lots of opportunity for bugs. On top of that, we have 1,100 pull requests into our Git today, and that averages out to something like 19 commits per minute. A lot of code velocity, a lot going on there. We, in addition, have 3,600 different developers committing to Windows. Not all of them are great at security, I'm going to tell you that straight out. And then, of course, there's 440 branches because there's all sorts of different projects. So when inevitably people ask me, how did this bug get through? I made this slide to point this to them, which is, this is a very difficult and challenging job, but I think we're up to the task. On top of having lots of code, Windows itself is evolving very quickly. So it started out, probably most of the ways that you experience Windows is on the desktop. Probably some of you are still running Windows 7. You play a couple games. You've got IDA open, whatever it is you do. But in reality, Windows powers lots of things today, from the conventional desktop PC to running Xbox to IoT to HoloLens and the cloud and just about anything you can imagine. And so just because you have code that you're able to secure in one environment, we all know once that's converted into a different use case, things can change very rapidly. A great example of this is I can remember 12 years ago, we didn't think anyone would be crazy enough to put the DirectX on the attack surface. Nowadays, remoting graphics is a very common thing, and the threat model changes very, very quickly. So it's really important to understand and take advantage of this. And so when we think about the Microsoft of 15 years ago, we were just getting our feet wet on what was essentially our security process 1.0, or SDL. It was very much locked into this kind of waterfall model. It was like, we're going to spend 3 months speccing, we're going to spend 5 months doing design review, then we're going to write it all in a Visio document and have an SDL. The reality is that worked pretty well when we had 3 and 5 year development life cycles. Now, I'm lucky if I get 3 to 5 weeks. We're actually getting updates with features. We're constantly revising and distributing the operating system about twice a year. So this type of process simply isn't going to work going forward. We learned a lot from it, but we want to take the best things that work well and create a more agile process. And so our evolved strategy is really, I think, the best of what we learned from those days and honestly learned through a lot of battle scars. So we really have 3 key points, and all of it is grounded actually in intelligence, understanding things. Because back to the concept, Windows is so gigantic, the reality is even if we had an army of 10,000 security engineers, we couldn't review every line of code. So instead, we need to be really, really intelligent about where we focus our resources and what we ask our developers to do. So we do that in a couple ways. The first basis for that is threat intelligence. So we use a lot of what we can detect from implants in the wild, exploitation, approaches that we see from attackers, and we create a risk profile based on that that will allow us to figure out where we want to have our security engineers spend their time. The second thing is obviously red teaming and our own internal efforts at mimicking attackers help a lot, and then of course community events like this. And from that information, we focus in 3 different areas. The first is we want to scale to developers. Those 3,600 people, we don't just want them to commit code, we actually want them to engage in security testing. So we provide scalable fuzzing infrastructure, know-how, static analysis, etc. Number two is we want to take our security talent, the security engineers who are a relatively small ratio when compared to developers, and we want to focus them in the areas that matter the most. And then number three is if we see a repeated mistake, we want to invalidate that mistake by moving to safer languages, updating the operating system, or changing the compiler. And I'll show you some examples of that. So the way we think about this is there's really a discovery funnel that we want to focus our energy on. The idea is we want to mimic the development lifecycle and figure out where's the best place to apply the right technique. So if you think about code starting with a pull request, we want to have static analysis that catches bugs as early as possible, because that's the cheapest possible point. Now, anybody who's ever worked with static analysis knows that it can be noisy, it can be nasty, etc. But if you can just trim off a few of the common bug classes very early at the compiler or static analysis, those are things you don't have to go hunt down later. Similarly, at the unit test or build integration perspective, we'd like to be able to automatically generate fuzzing, enumerate attack surface, and give feedback to those developers. And once they're ready to actually test their code, and most often that's internally, we want to use things like ASAN and dynamic analysis to catch, again, more low-hanging fruit with some of those techniques. And that really leaves our pen testers and our red teamers to focus on the places where developers simply aren't going to have the expertise or the history and skill set to target that. And that's why we want to create this funnel that will allow us to focus our resources in the most valuable places. So the first question is really, how do we scale security in Windows? The challenges of scales are enormous. The first is, fuzzing is great in concept, but a bad fuzzer is not worth very much. So the question is, how do we make an average developer fuzz like a rockstar security engineer? That's a real challenge. Number two is static analysis sounds great. It sounds great in practice, but in reality, it has lots of challenges from a precision standpoint. It can take up resource. Configuring it is challenging. So in practice, rolling it out at the scales we're talking about is a ridiculously challenging engineering problem. And the last thing we want to do is make it super difficult for you to shoot yourself in the foot. So beyond just things like banning certain APIs or having basic kind of hygiene approaches, we want to be able to instrument the compiler and other places to simply remove concepts that developers tend to get wrong, especially when they have to move fast. So the first thing we need to do is focus the organization on where there are challenges. When we have so many commits happening, the first thing you have to ask yourself is, where is code being introduced that actually has some risk? So we address this by actually creating an automated system for automatically enumerating attack surface, and we call that Waze, or Windows Automated Attack Surface Enumerator. And essentially what it does is it takes every single build that is a candidate for flight, it sets that build up in a VM environment, and it runs a combination of static and dynamic analysis. So it can actually use some of our DBI frameworks to figure out at an argument level whether a parameter is changed to a function, whether there's a new RPC interface, did a new ActiveX control get added, is there a DCOM interface, is there a new ioctl, et cetera, et cetera. And we take that information and we generate fuzzing tasks and requirements on our developer, and that's the first level of scale. Here's just an example of what we can get out of this waste database. What you can see is we have an enormous number of system calls, 1,700 in total, and just in the last OS, we added another 84 system calls. So Waste will automatically discover that and generate, in some cases, syscaller stubs or other test collateral that will allow us to automatically go and put some security engineering muscle onto these critical attack surfaces like the kernel. Now, it's one thing to have the attack surface. Another thing is to actually get quality security tests. The way that traditionally works is someone sort of figures out their threat model, which can be challenging in and of itself. I remember one time I was in a threat model meeting where we were discussing the risks of a function that returned void. So that's not a great use of resources. So we want to really focus our developers on places where they can make a difference. The second thing is they might write the test harness, and develop fuzzing on their own. And that can range in quality tremendously depending on the experience and skill set of the developer. So here's a great example of where it worked well. We actually had an agent across a hypervisor boundary that handled DHCP traffic. So what we were able to do with this particular developer is they took all their mocks and stubs, they redirected a lot of the code exercised into libfuzzer, which generated quality test cases for them. The performance and throughput was tremendous. We actually got 200,000 iterations per second on this self-contained parser. we landed on 72% code coverage. We found 4 vulns and 2 RCE remote bugs in a brand new DHCP stack. This is exactly what we want to see, and this is done by a developer who doesn't have any security expertise, just by having quality tools. So this is a great example of how it can be done manually. The question is, how do we make developers rock stars so this is just simple to do? How do we make this easy? And our approach to this is actually to take the Microsoft Risk Detection Platform, or MSRD, which is actually a platform built on top of the Azure cloud, which extends all of the tools that we use internally to Microsoft to external folks. And so the use cases are pretty simple. You provide a fuzz target or a binary or a build of the thing you'd like to exercise or fuzz. You give us symbols and as much metadata as possible. You give us a test harness to exercise that code, maybe with a specially named function, and any corpuses or metadata, whether that's packets, API calls, files, depending on the fuzz surface. And MSRD abstracts all of this and provides hyperscale fuzzing. And really, when you think about the quality of fuzzing, it comes down to a few things. One is the quality of your test cases, the quality of your fuzzer, and then how fast can you scale that. And we aim to solve all 3 of those problems in this MSRD system. And so, for example, a developer can simply mock up a test, and they can run libfuzzer. They can have syscaller stubs automatically generated from symbols, and we can even use concolic or constraint-solving fuzzing to get deeper code coverage than would be possible, and it's really difficult to configure on its own. So this system is actually plugged directly into the engineering systems in Windows, which would allow you to simply, in your daily workflow as a developer, generate hyperscale fuzzing with quality security features in it. So let's look a little bit about some of the fuzzers that have been integrated. The first one I want to point out is a fuzzer called Sage, which is actually developed by our research organization. And what Sage does in a nutshell is it converts all of the code paths that are controlled by tainted data into an elaborate mathematical function. So what we can simply do is use a Z3 or constraint solver to convert those code paths into a solvable math problem. And the Z3 constraint solver will generate inputs that can solve that function, leading to code coverage and state coverage. So if we look at this very basic function, you can see if you're able to submit the string bad exclamation point, you'll actually drive up the count to 4 and trigger the crash function. Now, this is a simple example, but in reality, this is very much what it would look like to exercise a simple protocol. So what Sage will do is start with an initial input, maybe good. It will generate constraints for all of these if statements and understand that because of taint tracking and dynamic analysis, it has control of that input across a trust boundary. And it will go through a series of generational approaches using the constraint solver until it finally generates the input that would net new basic block coverage. And in this particular case, that basic block actually leads to a crash. So that's a simple way of where someone can start with a test stub that maybe has 10% coverage and end up with 90 or 100% on the tainted surface. Now, the second thing we want to do beyond this sort of fuzzing dynamic analysis, we want to provide static analysis at scale. We do that in 2 places. First is on the developer's desktop for high throughput iteration. We run a number of rules there, actually 147 across 7 different engines, and we find bugs there early where they're cheapest to fix. More sophisticated static analysis is run directly in the engineering system, where it has to deal with a lot more scale and performance issues, and that's run basically every time a build is generated in Windows across those 400 branches. So very quickly, every time a pull request goes in and that gets submitted to a build, we actually run 2 different types of basic static analysis. The first is AST, or abstract syntax tree prefast, which is something you might be familiar with from Visual Studio. But we also bought recently at Microsoft a little company called Semel in GitHub, which has a very different approach to static analysis. And we're now starting to scale up our Semel rules, which have been very valuable. The thing I wanted to point out here is 2 things. First is to do static analysis on a single build of Windows, it takes 56 VMs running for 24 hours. It's a pretty big scale engineering problem. Number 2 is, even though a lot of these rules are noisy and they might be limited in scope, we generated 8,000 bugs and 2,700 different defects fixed in a single calendar year. So it is really effective at this scale for, again, eliminating some of the more basic issues. An example of how this can be made even more effective is something we call SAL, or Source Code Annotation Language. In the basic form, running a generic static analysis capability, we're often lacking information around context. So for example, as a developer is writing their code, they might be able to add annotations that are specific that would tell things to the static analysis engine like, hey, this type of behavior should never happen. If this particular value goes out of this range, then you should flag a contract violation. And I wanted to give you an example of where this can actually net quality bugs. So what you have here is a basic vulnerable function. This is actually a 0-day that we found in a particularly scary network stack. And an interesting contract violation here is vulnerable function returns just a buffer that's 2 bytes, but it's actually assigned to a header structure that's 16 bytes. And so when we dereference the ID field of that header structure, we're actually going to go out of bounds. So static analysis on its own didn't catch this because of the intra-procedural nature, but as soon as we added this SAL annotation here that tells when a contract is violated and by what size the buffer is expected to be, we actually net out and find this issue. So here's a great example of a bug that could have easily be turned into a wormable thing. It's the next sort of marketed headline-driving vulnerability that's eliminated pretty simply in our engineering systems. So we aren't limited, actually, at all for static analysis engines. Most of our limitations are in writing quality rules and getting the noise level down to something that's acceptable to assign to developers. I mentioned we filed about 8,000 bugs, only 2,700 were fixed. If we employed all the latest and greatest plugin techniques, we would probably drive that noise ratio way up, and developers would trust our tools less. So the constant battle we fight is pretty similar to the battle you would fight in, say, developing an EDR, which is if you make it too noisy, no one will look at the alerts. If you make it too scoped, you'll miss all the good bugs. So the reality is we have lots of different frameworks, but we're constantly battling with how to tune them into a way that we can get more actionable bugs, which is the hard currency we care about. And then finally, I look at static analysis as a really good proving ground for something that should be in the compiler. If it's something we can catch reliably in static analysis, I'd like for that condition to just not be possible at all. So we have a great relationship with our Visual Studio team and open source compilers like Clang and LLVM, where we're able to convert more of the things that we see regularly, mistakes at the developer level, into compiler changes. So I wanted to highlight 3 areas in which we're looking to make sure that developers can't fail. The first is a lot of investment in memory-safe languages. There's lots of experimentation for things like Rust in Windows, where we're looking at how do we take these newer systems languages and apply them to critical code bases. So if you're a fan of Rust, you might have been following some of the blogs coming out of MSRC, but a lot of activity and energy there. Similarly, we are using some of the C++ standard library updates for constructs like span, which make it much simpler to deal with binary buffers without doing a bunch of sophisticated pointer math that can rely in things like out-of-bound indexes or integer overflows. And GSL span is something we're using quite widely in high-risk code bases in Windows, specifically in places like Hyper-V. And then the last thing is we are updating some of our allocator wrappers, in this particular case, xallocate pool, and we think this will solve a lot of the habitual problems we see in kernel code that's related to buffer handling. Okay, now that I've talked to you a little bit about scale, let's talk to you about how we make our precious security engineering talent who are hunting vulnerabilities in Windows more efficient. So there's really 3 big challenges to doing vulnerability hunting. The first is we only have a very small number of security engineers relative to the giant army of engineers. And no matter how many we add, we'll probably never have enough. So having a good strategy on where to deploy them is a never-ending problem that we're constantly tuning. The second is, because these folks are scarce, we want to make every time they do an engagement as valuable as possible. So there's a lot of discussion on how to create tooling and frameworks that will result in more efficiency there. And then last piece is we want to understand how effective they're being. If we're deploying our best security talent somewhere and they're not finding bugs, we want to make sure we're moving them somewhere else. So prioritizing security reviews is honestly just a dark art. We have a pretty simple way we think about deploying, but we're constantly tuning this, and you can be caught off guard. So for example, we'd like to make sure that we're always deploying folks in the area of highest impact with the highest probability of a vulnerability being found externally. Why is that? We know we're not going to find all the bugs, so what we want to focus is on finding the bugs that are most likely going to be converted into exploits, and I bet a lot of you are thinking in your head, how would you do that? How do you predict that? And the answer is it's very challenging. So we use a couple of different data sources for this. The first is, we kind of have a lot of data coming into Microsoft on what attackers are actually doing, at least in the raw sense. So we can take a lot of those threat detections, break them down, and figure out what surfaces are most interesting. The second thing is we can actually look at zero-day exploits as at least a proxy for how good we're doing. So if zero-day exploits are trending down, even if bugs are trending up, we can say things like, well, we're adding the right platform mitigations and we're finding the right bugs. Now, the challenge with that is we're not going to detect all the 0 days. There's plenty that we probably miss. But again, we're constantly looking for better data sources that are going to tune us into very specific areas. But probably the best source of intel that I get is probably going to be here at this conference where someone's going to knock me over at the side and say, have you looked at this function? You guys are doing a terrible job on this binary. And I'll take a lot of that intel and we actually convert it back into security reviews. Some of the best stuff I find is actually through relationships in the community or through bounty participants who are giving us information on how to improve. So here's a great example of where we would deploy security reviews. Hyper-V, kind of important. You might think, hey, pen testing Hyper-V, how difficult can that be? We understand the security boundaries. In reality, the threat model for Hyper-V looks like this, and I would say that this is a very generous summary of what the attack surface actually looks like. We've got dozens of virtual device modules. We've got multiple different architectures, all with slightly different hypervisor design. We've got Gen 2 VMs, Gen 1, all which have different components. So this is actually an example of how our security team would look at the different components and make sure that they're scheduling security reviews as those are updated. Meanwhile, as we're pen testing this, new code is constantly coming and changing. So I actually want to take you quickly through what it's like to do a pen test in Windows from a manual standpoint so we can tell you how we're improving that over time. So TLS 1.3, pretty critical in Windows. This is the new protocol we just implemented for the new standard. It secures most of communications in Windows, thus the world. Really enough said about the risk there. So the first thing you have to do when you're trying to do a pen test in Windows is you've got to get a test environment up. As a pen tester, this is a lot more challenging than you think. You got to go knock on a dev's office. You're like, where's your test cases? Do you have test collateral? Do you have protocol documentation? Depending on the dev, they're going to say, like, talk to the hand. I'm busy trying to land this code by a certain date. So actually just getting up a debugging and test environment is the first hassle. It's actually a lot of work. The second thing you want to do is, again, you're just being handed a big blob of code, and if you're lucky, a spec. So the question is where do you focus yourself? Thinking back to that big map. Maybe you're a security expert, but you're not an expert in TLS. So trying to figure out where things matter the most is very complicated. So this is the first area where we can have some level of automation. So we have great code search tools that will allow you to scope down, look for particular API calls, pretty similar to what you might get in something like IDA, but very targeted towards source code. And then we're fans of tools like SciTools Understand, which will give you metrics and other things that might allow you to manually determine places where there is risk. So here's an example of a heat map we generated from TLS 1.3. This is in SciTools Understand. And some of the things we're looking at here are, hey, what are the functions with the highest cyclomatic complexity? That might be an indicator of risk. Maybe that's a place to start focusing. So once you have a test environment up and you have an idea of where to go, maybe you're going to set up a just basic fuzzer to get things going. In most cases, you're going to get really shallow coverage. In the case of TLS 1.3, it's a really complicated protocol, so sending a bunch of bytes to an endpoint is probably not going to get you very far, but at least it gets you to understand if your test environment's working. Fuzzing phase 2 is where we will actually start doing more specific things. So maybe now we're creating a harness, and one of the things that we're really interested in for a remote protocol is, are we covering state? So if you were to just look at block coverage, you might think, yeah, I got 80% block coverage, everything is great. But if you're not covering all of the different permutations of that state machine, you're not doing very much to fuzz protocols ask me how I know. There are plenty of protocols where we have great block-based coverage or line-based coverage, but we'll get MSRC cases in them afterwards. So kind of getting that going is important. And again, part of being able to do fuzzing well here is being able to disable integrity checks and other things that would get into your way. So just being able to say things like, can we disable HMAC during testing, are critical components to success. So fuzzing phase 3 is where things get a bit more serious. We're pretty happy with our fuzzer. We want to do an optimization pass. And we want to make sure that we're not leaving any bugs on the table. So using something like ASAN to instrument some of the critical functions will make sure that we're able to get more bugs than we would normally. And it will increase some of the classes for attack. One thing I wanted to call out here that I think is pretty novel is previously, we really didn't have a good way for detecting information leaks across a remote protocol, which are critical to vulnerabilities like Heartbleed or just general primitives and exploitation of a remote protocol. So we've actually started to build instrumentation that will allow us to hook syncs and do some information leak detection. We'll look at the buffers not just being sent out, but the buffers coming back with sentinel values that will allow us to do information leakage detection. Static analysis will obviously happen. This is a place where we actually leverage SEML internally pretty heavily. We find it's actually a great tool for guiding pen testers into more additional places to look while that fuzzing is going. And then finally, we'll start to do a lot more deep instrumentation around code coverage. This is a place where you can wait for a code coverage build that's going to happen massively, but often pen testers just want to be able to very quickly make an adjustment to their fuzzer and get immediate code coverage. So we're often looking at some of the code tools that might exist out there in IDA land and other places. Yes, we use IDA Python, Lighthouse, some of the common plugins. And then finally, we want to take some of this collateral and give it to the feature team so they can leverage it. So for TLS 1.3, this was a lot of work, but it actually paid dividends. Here's an example of a protocol we're just now turning on in customer environments where we actually found a double-free RCE before it got out into the environment. So this is a good example where the manual cost here was probably worth it. We want to see how to up-level it. And just so you know I'm not talking crap here, here's actually a demo of the bug. So what we're going to do here is just fire up a browser. We're running a TLS 1.3 IIS server in the VM. So we'll just connect there, simple hello protocol, and now we're going to man in the middle of that traffic. The reason this crashed, probably some of you can guess, is knocking down TLS, in this particular case, knocked down LSAS, so this device is now in a non-normal state. And as I said, this is a good example, I think, of a positive case where we found the bug before it got out there, but many cases that is challenging to do depending on the complexity of the protocol. So I've showed you a lot of the manual work that happens there. The real question is how do we get rid of that so we can find more bugs, which is our goal? And to do that, we've actually built a full-featured security research platform. So a couple of interesting things about this platform. One is internally we call it TKO. We wrote it in Rust because a lot of the code that needs to be pushed here is pretty similar to a normal environment, and it would be embarrassing if the security team had memory corruption issues in our test environment. So we built it in Rust to get a feel for whether or not Rust is ready for production, and of course, to eliminate some of that. The second thing is we wanted a couple of requirements. The first is we wanted guaranteed 100% deterministic repro of even stateful-based crashes. So what that means in a nutshell is we chose to build this on Box, a full system emulator, which would allow us to get a VM into a state where we have most state coverage, and then trigger the fuzzer once the VM is in that deterministic state. Beyond that, we wanted to be able to create plugins for things like crash bucketing, code coverage, corpus management, and all the basic things that exist today in a bunch of disparate manual tools in a simple place. On the last bit is we wanted to be able to take something that's running on a researcher's desktop and effortlessly move it into a hyperscale cloud, and TKO fills all of those requirements for us. So the first interesting thing about TKO is, like I said, it's built on Box. It's about 1/100th of native speed, but the fact that we get 100% reproduction and that we can snapshot fuzzing at any given time is incredibly valuable. And we've been able to build kernel debuggers on top of this, basic fuzzing frameworks. We've implemented things like syscaller and libfuzzer on top of it, and we have a runtime API that makes this super easy to extend it in Rust. So here's a great example of a case study of accelerating variant finding on top of TKO. So in July, GPZ reported 5 different MSRC cases in the PE file format. So it's very clear we have a challenge in PE and we want to find more. So we built a simple PE fuzzer on top of TKO. And what TKO gave us the ability to do was actually snapshot the system once we're pretty deep in the PE fuzzer parser state, and then do dynamic mutation, iteration, and code injection starting from the point where the PE parser is already pretty deep in code coverage. The result of that is not only did we find all of the MSRC cases that we previously missed, but we found one additional bug all within 3 days of the initial report. So here's a really simple example of how easy it is to take a TKO snapshot. So you can build a test harness that drives the system state into where you are ready to be fuzzed. Maybe you have to send 5 or 6 different initialization APIs. Maybe you have to load a particular PE with a particular header. But essentially all you have to do is fire off a particular CPU ID. And that CPU ID has a handler that will trigger a snapshot. And so in a few lines of Rust, we're able to immediately take a full system state snapshot, which has guaranteed reproduction. Here's what a TKO fuzzer looks like. You can actually set a mutation callback, and that can be on a particular instruction, breakpoint, system state, etc. In this particular case, we're just fuzzing the PE structures in memory. We can also set things like breakpoints. Again, breakpoints in a conventional world where you're using a programmatic debugger can be really difficult because you don't have snapshotting and some of those other constructs. And TKO, that's a breeze. You basically just take a callback on whatever particular memory, read, write, physical breakpoint, whatever you want, and you can trigger fuzzing from that. So here's an example of taking that previously super manual challenge around TLS and converting it into something trivial to do in TKO. In this particular case, we just wanted to instrument how often a particular function that controls TLS state is called, whether that's read or write, and what the particular structure was at that time. And so something that took us days of instrumenting normal code is actually implemented in just a few minutes with, again, 1/100th scale, which is pretty impressive and solves a pretty challenging problem here. Here's another example where we utilize TKO to do things that used to be really challenging. What you see on this heat map in blue are reads from a Hyper-V guest to a host, and what you see in red are writes. And what we're actually able to do with TKO is find out places where we're double fetching. So we're able to read information, and then before we process it or we go back and read it again, a guest can change that information to a buffer that we can no longer validate. So we've had a number of double fetch issues over time in the kernel. They actually manifest themselves in Hyper-V as well, and they're very challenging to find. Traditionally, they take a lot of code review or manual effort with static analysis. With Hyper-V and TKO, they're pretty trivial to find, and this heat map gives us exactly the place we want to look in the code, or we can simply build a fuzzer on top of. So beyond just this type of pen testing where we're looking broadly for vulnerabilities, we also focus ourselves on red teaming quite often, and the goal here is a little different than what we would seek to find in just standard pen testing. So I wanted to give a quick case study on how we found a vulnerability that's been called externally Deja Blue in RDP. So I wanted to quickly refresh folks on why we do red teaming at all. In essence, what we really want to do is not just make believe, but we want to model the way that attackers would operate as closely as possible. That allows us to test our mitigations, innovate internally new attack techniques, and generally get stronger metrics on how well we're doing in the real world. We also do things like identify security gaps in detection that are beyond just what we seek to remediate in the platform. If we build an exploit, we can actually share that with our blue teams who build detections on top of this. And again, this might give us a probabilistic model for detecting a vulnerability or a technique we have yet to see in the real world. And then finally, we're able to take some of this information and in places like One Hunt, which is our annual red blue team event, actually create a sort of a pseudo incident or a mock incident and see how well we're communicating, how well our information is exchanged, and really demonstrate the real world impact. So RDP was actually a place where we know in many cases these ports are exposed and they're used within our own infrastructure, so we were really concerned about a number of RDP scenarios. Most of you are probably familiar with some of the recent RDP exploits that target server side, but there are actually a number of scenarios where you can attack from a potentially malicious server back to the client that might be interesting. The first is if an attacker could get on a jump box and send back an exploit from that jump box to clients, you could target high-value assets from a jump box. In fact, that's something we've done in Red Team Tradecraft previously. And then increasingly in Windows, we're using RDP to interact with containers or other local VMs where the client itself is actually the trust boundary. So the server exists inside a VM and the client exists on the host. Those are both scenarios we wanted to test for. So we went ahead and targeted the client code, and in essence, we found lots of interesting things. So from a single Red Team case study, we found 9 critical RDP vulnerabilities and 3 important. Those are the CVEs up there. One of them is called externally Deja Blue. It took 33 days in total to weaponize that exploit on Windows 10, 13 days to find the bugs, 20 days to actually write the exploit. And that includes bypassing a lot of the mitigations that are native in Windows 10. So I wanted to show you 2 of the primitives that we pulled out of this. The first is a memory write, which is, again, the Deja Blue vulnerability. It's in the custom serialization layer of RDP. And you can see, in essence, what we have here is a fully controlled size to a mem copy, and that gives us an arbitrary heap corruption of attacker-controlled length. So pretty powerful primitive. Now, just writing over a remote protocol is not enough. We either need to take that write and convert it to an information leak, or in this case, we had a second bug. In this case, it's an arbitrary read. So again, we control, in this case, the source pointer from a mem copy that's copied back to the attacker. So we can leak arbitrary memory, including uninitialized heap data, which is a primitive that's critical for rebuilding the remote code execution exploit. So this is what it looks like to actually build the Deja Blue exploit. Stage 1, we're doing LFH heap preparation. Stage 2, we're doing some information leakage. Stage 3, we're taking the information leak pointers and creating an arbitrary vtable call through that ends in remote code execution. But rather than showing you a Visio, why don't we just look at the exploit in practice? So you can use here, we're using Kali Linux, which is our preferred exploit environment. And we've got a malicious server and a trusted client. So we're actually going to connect across, of course, say yes. We're now triggering both the read and the write, and we have full code execution in the client at admin. So again, thank you. So if this was a jump box or a sentinel box or anything in a critical infrastructure, and I'm sure many of you either use SSH or RDP for this, then any client that would connect there would be fully exploited. So we've gotten a lot of information here from both our pen testers and at scale. The question is how can we iterate the platform to remove more of this from the battlefield, so to speak? So our first approach on things we've been doing recently is killing more and more bugs at the compiler level. So 2 great examples of this are init_all. So init_all automatically initializes local arrays, scalars, or structures to 0, which prevents basic information leaks, which are actually a pretty systemic issue traditionally in the Windows kernel, and we've been able to eliminate lots of those. So some great work there from MSRC and other folks who worked on that. It's now shipped in the latest Windows. And we're following that up with an additional mitigation that targets what we call type confusion bugs. So illegitimate castings are a real systemic problem. Again, pretty big ranker on the root cause around MSRC issues. And so we've built a mitigation called CastGuard, which looks for static casts of objects and prevents illegal downcasts, which are pretty systemic in what we see around type confusion issues. This code is feature complete, and we plan on shipping it in a future version of Windows. If you want a really detailed explanation, you can see some of the Microsoft talks from the recent CPPCon conference. So CastGuard, in a nutshell, essentially generates a bitmap that looks for downcasts that would be out of nominal range. You can see some of the basic assembly here. A lot of this is heavily perf optimized depending on the scenario, but here's a basic example. In this case, we're taking a void function pointer and we're casting it to our cast here that has a foo public function and a bar private variable. Depending on the attacker's control of that void pointer, they would now be able to point memory without CastGuard into a place that could be converted into code execution with CastGuard that actually can generate an immediate runtime error. Path mitigations are another place in which we're seeing some systemic issues, and I wanted to give you a good example of how we're addressing that in real time. So about 1/3 of all access control and half of all race conditions found in the last 6 months are related to illegal use of path. And what you can see is in 2015 to about 6 months ago, access control vulnerabilities were just a tiny part of the things we had to address. And just recently, in the last 6 months, you can see from that red there that access control is approaching about half of the issues we're seeing from MSRC. So this is a great example of where we want to take intelligence and create some platform mitigations. Obviously, developers are having a hard time addressing this as point fixes, so we think that's a perfect candidate for platform fixes. So let's talk really quickly about where this is coming from. So path redirection attacks and time of check, time of use have been around for some time, but James Forshaw of GPZ actually did some great work documenting how those can be used and produced some tool sets. So there's 4 different blogs here that really contributed to the community understanding of these types of issues. More recently, Sandbox Escaper has taken very similar approaches and found even more bugs in other system services. This class of issue really comes from time of check, time of use, so validating a file and then using it again without revalidating it, without understanding the attacker has full control of it after that point in time. And this is mostly targeted at high privileges services, which will allow what we call local privilege escalation. So I'll walk you through a canonical case of this. So in this particular case, Mallory makes a call to an IPC service that's running at system. Perhaps Mallory is running at standard user level and wants to achieve full local privilege escalation. So that service would impersonate or switch to context of Mallory to do an operation. It wouldn't be running at system, it would be running in the credentials of Mallory, maybe write a file. The service closes that handle, and then Mallory races to replace it, maybe using an op lock or some other concurrent signaling approach. And then when the service reverts to system, that file is deleted. So this is a really good example of how a privilege escalation based on path works in practice. Now the question is, how do we mitigate that? So we've actually got 3 different mitigations that we'll be shipping in a future version of Windows. The first is our hard link mitigation. That's going to require write permission to a linked destination before a creation. It's already out there in Windows Insider Preview, and it's bounty eligible, which is what I'm here to talk to you about. So if you want to take a look and find some issues in that, we'd appreciate it. Or if you want to tell us it's working well, that would be great too. We also have a junction mitigation. So newly created junctions gain a mark of the web, or essentially mark of medium IL. This will allow service owners to disambiguate where a file came from without running in a particular impersonation context. And so we'll be weaving that through Windows in a future version. And then finally, we're making a change to the way system temp is handled. So today, system temp's value is world writable, and we'll be making a change there for a new ACLed path. So that's great. This is a good example of where we're taking our best information from our own internal pen testing. The question is how effective are we being at this? And this is always a really complicated question to answer. So being able to say how many bugs we should have found or could have found based on our resourcing is a difficult question to answer. So a lot of our focus is on making sure that we're getting our pen testers and our developers as effective as possible and as efficient as possible. And one of our key metrics for that is our fix rates. So you can look back in 2018, just a year and a half ago, our fix rate was at a pretty miserable 38%. So that means of all the bugs we found, static analysis, fuzzing, reports, you name it, only about 38% of those were fixed. And there's a bunch of reasons why. Maybe didn't have the right detail. A lot of times fuzzers are non-deterministic, so reproing an issue is difficult for a busy developer. Static analysis is noisy, you name it. So with investments in better tools and a lot of things I showed you today, our fix rate is actually skyrocketed to, in 2019, 98% of all bugs, security bugs filed in Windows were actually fixed. So in conclusion, we're really evolving our practices constantly to provide the most secure platform. We're not just taking the template of SDL from 2004, we're taking the best of that information as well as the best of open source and what we can learn from the community to continue to evolve. The OS security team is not the only team responsible for security in Windows. We want to scale out to that developer army and convert them from folks that we see as generating bugs to folks as we see as partners in securing the operating system. We're constantly looking to improve our security research, how we measure it, where we focus it, what our tool sets is. Our goal is to be more efficient. And then finally, we want to take the best information we have on the trends we have to continue to make durable platform improvements. I've showed you a couple of examples of where that's happening within the compiler. That's happening in places like Hyper-V, where we're experimenting with components written in more safe languages. And of course, some of the things like path link mitigations are where we're learning from the community and getting better. With that, I wanted to close with, we're hiring, so if you're interested in doing similar work, come find myself or anybody else from Microsoft. But with that, thank you very much, Tel Aviv, and I'll see you soon.